Welcome. So in this video, we're going to discuss and present the notion of positive definite kernels on graphs. So the topic of this session is a bit different from the previous one that was kernels for graphs. In the previous one, we investigated how to embed the set of graphs in an RKHS, meaning how to analyze data where each data point was a graph. And in this lecture, in today's lecture, we do something a bit different. There are still graphs, but we assume that basically there is only one big graph that exists. And what we want is to analyze data which are nodes in the graph. Right? So it's not that we want to embed individual graphs in a Hilbert space. It's that one big graph is given, and we want to study data that lie on a graph. So needless to say, there are plenty of applications where we are confronted with such data. Just to name a few, there are a lot of big networks made, for example, of computers like the web, or it could be electric grids, network communication systems. There are the data like social networks, where basically each node of a graph is a person, and the edges of the graph correspond to various relationships, social relationships between people. Or there are other applications. For example, if you study life sciences, where you may study the set of proteins which are produced in a cell, and you know that the proteins can work together, and it's possible to describe the interactions between proteins again as a big graph, where the nodes of the graph are proteins and the edges mean that two proteins interact, for example, or work together. Right, so in all these applications, as you can see, the goal is not to embed the full graph as one vector, but to say that the graph defines a kind of geometry, or at least some structures on how nodes relate to each other. And what we would like to do is to work over nodes. So the kind of applications that we want to tackle, we will discuss a few of them later, but could be, for example, to do machine learning over nodes of a graph. Think of a social network. Suppose you have a social network that's given to you. You have some labels for some individuals in the network, and the question would be, can you predict the labels for other individuals in the network? So if you want to use kernel methods, or let's say linear models in some space, this means that what we will discuss and what we have to do is to map individual nodes of the graph into a vector space, so to represent each node as a vector, so that then you can use, for example, linear models over the vector representation of nodes. And so when we talk of kernels, remember that as soon as you define a mapping phi, an embedding of your nodes to a vector space, then it comes with a kernel, and the kernel between two vertices, so x and x prime being two vertices of the graph on the left, would be the inner product of their embeddings after you represent each node as a vector. All right, so what we're going to discuss now are basically what can we do in order to define these mapping phis or the kernel K. So the first comment is that you see that in this setting, the space over which we work, capital X, is finite, because the set of all possible data is just all the vertices, all the nodes of the graph. Right? So if the first constraint, if you want to say, what can I do to make a positive a kernel, so to do this embedding with the kernel, what you need to do is to define a positive definite function over the set X, and because the set X is finite, basically any matrix which is symmetric and positive semi-definite will work, right? It's a valid kernel. So we need something else, right? We could take any positive semi-definite matrix, but it doesn't mean that it will be any useful. And what we need to think about is, if I come back to this graph, how to do something so that the kernel captures something about the graph, and typically capture the topology, the geometry, the pairwise relationships that exist in a graph, so that when you learn something, for example, the position of the points, right, the white and black points here, reflects their position in the graph. Okay, so we need not only the constraint to be positive definite, but also to ask the question how to encode the structure of the graph into the mapping phi or into the kernel K. And so this is exactly what we're going to do. And what I take this opportunity to try to illustrate how we can follow different strategies when we need to define a kernel over some space like that. We will discuss in turn 3 approaches to make a kernel, and then we'll discuss their relationships. The first strategy is, let's say, the geometric one that says once you have a graph, it defines some pairwise relationships, something like matrix distances between nodes. So one idea could be, can I create a kernel so that the geometry in the Hilbert space approximates the geometry of the graph? That would be one approach. Then a second approach is a dual approach, which is quite natural, I hope, for you now that you have followed all the videos of this lecture, is that when you have a kernel, you can think of it in terms of the geometry of the points, or you can think of it in terms of RKHS, what is the space of functions it defines, and in particular, what are the functions and what's the norm of a function. And remember that for the method to work, basically, the norm of a function in the RKHS is supposed to capture something like the smoothness of f over the space over which it is defined. Which means that in order to define a kernel, maybe it's possible to start from the graph, to define what are the functions we want, to define what is the smoothness we want, and then to derive what is the kernel that induces that smoothness. Right? So this will be the second approach we'll follow. And the third approach, which is also possible, is in particular the case where you see a graph as a discretization of a continuous space. Right? Suppose you have, in fact, a true signal in 2D, but you just encode it over pixels or over a grid. Then you may want to say, well, in the continuous space, there exists plenty of positive definite kernels, like the Gaussian kernel, for example. How do I translate the Gaussian kernel from the continuous space to the discrete space with something like, if the grid becomes very, very small, then you would like the kernel on the grid to approximate the continuous kernel. Right, so this would be a third strategy, which would be to say, can we define a kernel by approximating what we know how to do on the continuous space and do it on the discrete space of the graph? Okay, so we'll take each of the 3 approaches in turn, discuss the relationship, and finally conclude with some illustration of how to use these kernels. So let's start with probably what's the most natural approach, especially when I show the picture of saying, you have the graph and you want to embed it, so map it to some feature space. The first natural approach is, can we just create a space where the distance, for example, the pairwise distances between the points, mimic the natural distance that exists on the graph, because the graph defines the notion of distance between vertices. And so to formalize a bit what we can do and the kind of thing we would like to do, remember that when we talk of kernels, a kernel is an inner product. So as soon as you have a mapping phi, then there is a kernel k of x prime, which is the inner product between phi of x and phi of x prime. But there is also, of course, a Hilbert metric that comes with it. You can define dk as the distance in a Hilbert space, meaning that you can define dk of xx prime, the square distance, as the natural squared Hilbert distance between phi of x and phi of x prime, which can be computed, of course, from k with the formula that we have seen many times, k of xx plus k of x prime minus 2k of xx prime. And so, we had a homework where we discussed something called conditionally positive definite kernels. It turns out that being, a Rungian theorem says that K is positive definite if and only if it's an inner product. And we have a similar story for distances. We can show that dk is a Hilbert distance if and only if it is equal to 0 when x is equal to x prime, and when it is conditionally positive definite, in the sense that, this is one characterization, in the sense that for any t, exponential of minus t times the distance square is positive definite. Right, we will not prove it here, but there is a homework where we do that. So this means that it's a characterization of what is a valid distance, if you want. And so this means that, for example, if someone gives you a distance and you want to say, well, maybe that distance, I can use it as it is because it's probably the distance in a Hilbert space. The way to check it is to check if the distance, so minus the distance square, is a CPD. Right? So, for example, the most classical things, distance is when you have data which are vectors and you take the inner product, then what I said just says that x minus x prime is indeed a squared Euclidean distance. We know that. And this is characterized by so this implies, in particular, that exponential minus t times x minus x prime squared, so this is the Gaussian kernel, is positive definite for any t. Right? And so there is also the converse. The previous slide was a bit the converse. It says that if exponential minus t x minus x prime square is positive definite for any t, then you can show that x minus x prime square is a squared Euclidean distance in some space. Okay, so how does this characterization match with our question, which was, can we embed a graph in a Hilbert space? So here the idea would be, if you're given a graph, like you give me a social network, then maybe there is these natural distances over the graph. And here we'll start with the simplest and most natural distance, which is the degree of separation, like the length of the shortest path between two nodes. So for example, if you're in a social network and you're connected to someone, you would say that your distance to that person is 1. If you're connected to someone who is connected to someone else, but there is no direct connection between you and the someone else, you would say that your distance to the someone else is 2, because you need to walk 2 steps to reach that person. Right, so more generally, this shortest path distance defines a metric. It's a valid metric between over the set of vertices. And so one question would be, can we just use this metric as a kernel? And so what I mean by that is that this is not an inner product, but could that be a distance from which we deduce a kernel, or for example, from which we make the Gaussian kernel? Just like, as soon as you have a distance here, you can make a kernel. Can we just replace the x minus x prime square by the shortest path distance over a graph? If it works, it's easy, because it means now you give me a big, whatever network, whatever graph, and you just, when you want to make a kernel, compute the shortest path distance, take the exponential minus t times this distance, and you have a valid kernel, so you can train a model. So, open question, is the distance conditionally positive definite, right? So is it true that exponential minus t times the shortest path distance over a graph is positive definite? And the answer is not really a full yes or full no, but it's summarized in this lemma. In general, it's no. In the sense that in general, if there is no particular hypothesis or constraint over a graph, if you take a graph and you compute pairwise distances and take the exponential minus t times the distance, then there is no reason why this would be positive definite, right? In general, it's not a valid kernel. Now, there are some cases which are not the general case, but particular cases where the statement is true, so where exponential minus t times the distance is a valid kernel, in particular when the graph has no cycle, it's called a tree, or where the graph is a single closed chain, or there are a few other cases, and we'll mention one of them later, which is a bit more exotic, but very useful, which is when the graph is the k-less graph of a symmetric group. Right, we'll detail it. Okay, but the main message is that in general, there is no reason why the shortest path distance should be conditionally positive definite. So, and we don't even need to go very far to find counterexamples. So here is a graph, which is a counterexample showing that if you're not careful, if you just say the shortest path distance and want to make a positive definite kernel, then you may just go wrong. So this graph has 5 nodes. I think it's not possible to find a counterexample with less than 5 nodes, but you're welcome to try. But at least this one, you see, what I say is that if you take this graph, then you can create the matrix of all versus all shortest path distance. So on the diagonal, you have 0, because everybody is at distance 0 from itself. And for example, between 1 and 2, 1 and 3, 1 and 4, you have distance 1. So you have 1, 1, 1. And between 1 and 5, you have distance 2. And you do that for all pairs. Now, what the question was, if you transform this distance by taking the exponential of minus t that you chose times this distance, you would get a new matrix, which potentially could be a kernel matrix. But here, if you do the computation, if you, for example, take for 2 minus 0.2, and if you compute the matrix of all the exponential minus 0.2 times these values, you obtain a square matrix, which is symmetric, that's okay, but which has a negative eigenvalue. So it's not a positive definite Gram matrix, so it's not a positive definite kernel. Right, so it shows that in general, the shortest path distance is not a valid Euclidean distance between nodes of a graph. Square Euclidean distance, I should say. All right, so I said there are cases where still the counterexample is not valid. So for example, maybe you can this is almost exercise you can do by yourself. So when you have a tree, for example, then it's possible to show that in that case there is no cycle. So you see here there are cycles. So this is not a tree. If I removed, for example, the node number 5, it would be a tree, and then the distance would be a Euclidean distance. Right. So if you have a tree, then you can prove that so there exists a space, an embedding phi that moves each node to a vector phi of x, such that the distance, so the shortest path distance between two nodes, is equal to the squared Euclidean distance between phi of x and phi of x prime. And so this slide shows exactly how you build phi. It's, basically when you have a tree, you pick arbitrarily a node in the tree. You call it the root. Then you define phi of x as a vector whose dimension is the number of edges in a graph. And by convention, phi of x is a binary vector where for any point x in the graph, you compute the unique path that connects x to the root. So you assume that it's a tree which is connected. So there is a unique path going from the root to the node. And for phi of x, you just put 1 for the edges that are on this path and 0 for the rest. And then it's easy to see that when you take any pair, so any two nodes x and x prime, there is the root somewhere. So each of them has a path to the root. And so when you compare the two paths from x and x prime to the root, you can imagine very well that they are the same up to the least common ancestor. So you have the root, and there is a least common ancestor between x and x prime, which may be the root itself. And then the two paths separate from each other. So when you make the difference phi of x minus phi of x prime, basically you will get 1s on the edges that connects x to the least common ancestor, minus 1 on the edges that connect the least common ancestor to x prime. You get zeros because it's 1 minus 1 over all the edges that connect the least common ancestor to the root. And at the end of the day, when you take the norm of this vector, which has 1s and minus 1s, then the square Euclidean norms would just be the number of edges from x to the least common ancestor and then to x prime, which is the shortest path distance between x and x prime. All right, a second example. So, here is in practice what I mean is that here is another graph. So you see, again, I have 5 nodes, but there is no cycle. So here it's possible to just like before, to compute all pairwise distances in terms of shortest path. For example, between 1 and 3, the distance is 1. 1 and 4, the distance is 2, etc. And then you take the exponential of minus these distances, and you could put any value in front of the d. You could put 0.2 or whatever. You will get a matrix, and it's a fact that this matrix is always symmetric, positive, semi-definite. So of course, you notice, for example, that because the distance between 1 and 3 is 1, and the distance between 4 and 5 is 1 as well, then the kernel value between 1 and 3 on the one hand, and between 4 and 5 on the other hand, is also the same. And you see it in a matrix. It's equal to 0.37 between 1 and 3, and to 0.37 between 4 and 5. Right, so that's an example of kernel which is positive definite, and which captures exactly the shortest path distance of a graph. But remember that this only works in this case because there is no cycle. If you have cycle, then you may have problems. There are a few other examples. I leave it to you to analyze. I mean, there is a proof and a statement here, but for information, if you have graphs with cycles, but if it's just one cycle, then in that case, the squared Euclid, the shortest path distance is a valid conditionally positive definite distance. Without looking at the proof, we can look at the picture because it will illustrate what I mean. In this picture, so on the left picture, you have a cycle of 4 nodes. So this is a graph with just 4 nodes and 4 edges. And you see that this is the case. So in this figure, we plot the graph in 2 dimensions. And this is exactly a case where the squared Euclidean distance in this 2D plot is equal to the shortest path distance if you define the length of one edge to be equal to 1. Why? Because if you take 2 successive edges, there are distance ones from each other. And if you take 2 opposite vertices, then the distance is a diagonal. And by Pythagoras theorem, the square distance between the opposite vertices is 1 plus 1, meaning it's 2. And this is exactly the shortest path distance. The same proof works in 3D. If you look at the next picture, I let you check that, again, using Pythagoras theorem, that the squared Euclidean distance in 3D between any 2 nodes here is exactly equal to the shortest path distance between the 2 vertices, right? And so you can generalize the proof easily to any dimension as soon as you have an even number of vertices. And in fact, the statement is also true when you have an odd number, and I leave it to you to think about that. Okay, so this means that, here we have cycles, but for these cycles, the distance can still be embedded in a Hilbert space. So here is a last, and I think a bit more interesting and a bit exotic graph. This is a graph which you can find on Wikipedia called the Cayley graph of the symmetric group of size 4. In fact, this would work for any n, which is not only 4, so for any symmetric group. So just to explain a bit what this is a graph where each vertex of the graph, so the set of vertices, is a set of permutations of, in this case, 4 numbers. So a permutation is just a way to rearrange 4 items in some order. You have the identity permutation, which we write as 1, 2, 3, 4, and it's written, it's one node at the bottom. And then you see, if you zoom a bit on this picture, you see that each vertex has a sequence of numbers, which are 1, 2, 3, 4, in some order, right? So in fact, all the possible rearrangements are in this graph. And we have edges between permutations here, and by convention, there is an edge between 2 permutations if they are equal up to an inversion of 2 consecutive numbers. So for example, 1, 2, 3, 4 is connected to 1, 3, 2, 4, because we have just inverted 2, 3 into 3, 2. And it's the same for all the things. All right, so this is a particular graph, and it's mathematically defined for any n. It could be not 4, but 6. We can have the same thing for 6. It's called a Cayley graph. And it has a particular interest because if we are able to define a kernel over the vertices of that graph, it means that we have a kernel over permutations, right? And so there are many, it's possible set of applications. In fact, there are several papers that study that, where sometimes you have data which are preferences or ranking or permutations, and having a kernel over permutations is a useful tool in order to do machine learning over preferences. All right, so the magic statement in this theorem is that is twofold. The first one is that when you take any 2 permutations over that graph, so take any 2 permutations, then it's possible to efficiently compute the shortest path distance. In fact, it can be computed in n log n. Think about that, but it's related to sorting in a sense, because moving from one permutation to the other raises the question of how you can go from one ranking to some other ones by just imposing that you do the least number of pairwise inversion of consecutive numbers, And to give you some hint, this is basically what's done by algorithms like merge sort. Right? So first statement, it's possible, given two permutations, you can compute the shortest path distance in n log n. Now, the second interesting statement here is that on this particular graph, even though it's not a tree and it has multiple cycles, it's a case where the shortest path distance is conditionally positive definite, meaning that as soon as you're able to compute the distance between permutation, you can take exponential of minus that distance, and you get a valid positive definite kernel. So maybe that's something you can think about it. There is a link to a paper that I wrote with a student, a former student of mine, Yunlong Zhao. And if you're interested, it explains in detail exactly all these concepts. But so in practice, this means that this is a used kernels that allows to do kernel methods over data which are permutations, and which is a particular case of Gaussian kernel using the graph distance using the Kelly graph. All right, so summary of that first part. Here we just discussed the first idea, which is that if you're given a graph, then the graph defines a notion of distances. Shortest path distance is a valid distance. And what we discussed is it possible to think of a kernel or embedding of the nodes in a Hilbert space so that the squared Euclidean distance in the embedding is exactly the shortest path distance over the graph? And the answer was, in general, this doesn't work. But there are a few cases, like the trees, the pure cycles, or the Kelly graph, and there may be others, where it works. And for example, in the case of the Kelly graph, this can even lead to efficient algorithms to define kernels between permutations in that case. Okay, so this was the first approach. Couple of comments. Well, one comment is that here we just discussed, can we embed the distance exactly in a Euclidean space? So the answer is yes or no. It's possible. There is a research direction, which is sometimes it's possible to embed approximately, like to find a mapping such that the distance in the Euclidean space is not exactly equal to the shortest path distance, but it's approximately equal, up to epsilon, etc. And so there is some research in that direction that you may be interested to look at to try to find good approximations of any distance. Second comment is that we just focused on the shortest path distance here. And if you're familiar with networks, then you may think that the shortest path distance is not always a very good distance. And in particular, it can be very sensitive to noise in the edges. Like sometimes, adding or removing an edge can completely change the distance between two nodes if the shortest path distance goes through that edge. So in a case where the graph you get, like if it's a protein networks, then we know a lot of edges, but maybe some of them are wrong and some of them are missing. Then it may be a bit dangerous to rely too much on the shortest path distance, because this distance is sensitive to noise in the graph, and probably more sensitive than other distances we will see later. All right, so let's move on now to a second strategy. So the first one was, we have a graph. From the graph, we take a distance, and from the distance, we try to find a kernel or an embedding that mimics the distance. Now we'll take the dual approach, the more functional analysis viewpoint, to say that when we have a graph, we forget about the direct distance between the nodes, but we think more in terms of functions defined over the graph, and how to define a regularization, a smoothness of a function over a graph. So in particular, we will directly try to make what's called an RKHS. Remember that an RKHS is a Hilbert space of function. And so here, just like we did already in the past with, for example, the Sobolev spaces, we'll say what are the functions we would like to see in the RKHS, and what's the notion of smoothness we would like to encode. And then we will see if there is a kernel that creates that smoothness. So in order to develop this idea, let's first introduce a couple of notations, because we will use some matrices and vectors. So here we assume that we're given a graph with m vertices. We call the vertices x1 to xn. And the graph, it's not directed, so we just use the notation x tilde x prime to mean that x and x prime are connected by an edge. We assume that when x is connected to x prime, then x prime is different from x. There is no self-loop. And in all this section, we would assume that the graph is connected, meaning that it's not like there were two different subgraphs that are not connected. Of course, we could do everything in a more general setting, but it would just simplify a bit our exposition, to assume that it's connected. All right, then let's start with two important notations. So one of them we already saw last time on the kernel 4 graph is the adjacency matrix. So here we have a single graph. So the adjacency matrix of the graph is just a big, if m is big, it's a big matrix, square matrix of size m times n, which is binary, which is full of zeros, basically, and which only has ones. So aij is equal to 1, if and only if I is connected to j. All right, so it's a way to encode the structure of the graph over the m vertices. The second matrix we'll use is the degree matrix, so we call it D. It's a diagonal matrix. So again, diagonal means that it's 0 everywhere except on the diagonal. And on the diagonal, dii is equal to the number of neighbors of xi. Right? So in particular, it's the sum of aij for, there is a small typo here, is the sum, so dii is the sum of aij for j equal going to from 1 to n. So, visually, this is what we define. When you have a graph, you can encode it into A, and from A, you can deduce D. A is binary, encodes the presence of edges, and D is diagonal. And it says, for example, that the edge 1 has one neighbor, not 2 has one neighbor, but not 3 has 3 neighbors, which are 1, 2, 4. Right? It's encoded here. All right, so from these two matrices, we'll now make a third matrix, which will be important in the rest of the course. Try to remember that one. In fact, it's important in many fields of graph theory. So it's good to know it. It's called the Laplacian of the graph. And it's defined just as D minus A. So it's simple, right? We have D, we have A, so we do D minus A. What does that mean? It means that on the diagonal, we just recover D, because A was 0 on diagonal, so diagonal term is D, is the degree. And on the off-diagonal entries, because D was diagonal, it does not contribute, so we just have 0 or minus 1s, and we have minus 1s when there is an edge between two vertices. Right, so this is the Laplacian matrix. We will say a few words about why it's called the Laplacian later. But something maybe you can already notice is that if you do the sum of the Laplacian matrix for each row or each column, you always get 0, because you have a positive number on the diagonal, which is how many neighbors you have, and on the off diagonal you have minus 1 for each neighbor. So the total sum, horizontally or vertically, is always 0. Okay, so the Laplacian is important, and before going to the RKHS, etc., let's prove a few properties of the Laplacian matrix that will be very useful to derive kernels. So again, here we assume that the graph is connected, and then in that case, we have the following 4 properties. The first one is that when you have any vector f, so f is a vector of size m, or you can see it as a function from the vertices to r, but it's a vector. Then when you compute f transpose LF, so L is an m by n matrix, so you can multiply it on the right by a vector, on the left by on the right by a column vector, on the left by a row vector. It gives you a real number. Then that real number is equal to something you can write down explicitly as the sum over pairs of connected vertices, so over ij which are connected, of the difference f of xi minus f of xj squared. Right? So it will be just calculus to prove it, but you can already start thinking that this starts looking like a measure of smoothness of f, because what you do, for this to be small, for example, what you want is that f of xi and f of xj are similar, so the difference is small, when the two nodes are connected. All right, so this function seems to measure something like it is small when f doesn't change too much when nodes are connected to each other. It seems to be like a notion of smoothness. Second property that we will derive from the first one is that L, in fact, is a symmetric positive semi-definite matrix. So this matrix is symmetric, you see it, but it's also positive semi-definite. It has 0 as an eigenvalue with single multiplicity and associated to the constant eigenvector. And the image of L, so the set of LF, when F is any vector, is the set of vectors with 0 mean. So let's prove this lemma. There is no difficulty. It's going to be quick. So maybe the only important one is the first one. It's good to do it at least once by yourself to be convinced. So when you compute, you start from a function defined over the vertices, and you compute the sum of fi minus fj squared when I and j are connected. You just develop the square, then you decompose the sum. You have 3 terms. You see that you have f of xi squared, which is counted a number of times equal to the degree of f. Then you have the pairwise product f of xi minus f of xj, which is counted each time you have a connection between I and j, and there is a 2 in front of it. And so when you factorize it and you rewrite it in matrix form, you obtain f transpose df minus f transpose af, and this is why we see the d minus a appear. This is the Laplacian matrix. This is equal to f transpose L. Now, the rest of the properties are easy consequences of that. So the first, we said that L is symmetric. This is just because A and D are symmetric. Therefore, if it's symmetric, it has real eigenvalues. The fact that, F transpose LF is equal to omega of F, which is obviously always non-negative, shows that all the real eigenvalues of L are non-negative. Right? So this means that F is positive semi-definite. Otherwise, it could take negative values. The next point was about the eigenvectors. What are the eigenvectors associated to the eigenvalue 0? So is 0 an eigenvalue? And what are the eigenvectors? Well, again, we can use the characterization that 0 is an eigenvalue with eigenvector f, if and only if f transpose LF is equal to 0. So we need to solve this equation and see if there are non-trivial solutions. Now we can use the formula for f transpose LF that we have just seen. So it's the sum for I connected to j of fi minus fj squared. If we want this to be equal to 0, it means that all the terms in the sum have to be equal to 0. So this means that f of xi must be equal to f of xj as soon as I is connected to j. And so because the graph is assumed to be connected, this means that all the vertices should have the same value. So this means that f is constant. And it's an if and only if relationship. So this means that 0 is indeed an eigenvalue, and the eigenfunction of 0 is just a constant function. Right? So this is multiplicity 1. Finally, the last point, let me show it again. It was about the image of L, which we say the image of L, so the set of LF is a set of functions with 0 mean. This is a direct consequence of the fact that because L is symmetric, it has real eigenvalues. So we can decompose the full space as the kernel of L, so the null space of L, and its image, and the two are orthogonal. And here we characterize the null space of L, which is a set of constant functions. So this means that the image of L is a subspace orthogonal to the constant function. And being orthogonal to the constant function is exactly saying that f transpose the constant vector is equal to 1, and this is just the sum of f of xi. So this concludes the proof. Now, using this preliminary result, we can now finally write down a theorem that relates the graph and the Laplacian and in our KHS, and that reads as follows. So here we consider the space capital H of vectors, but remember again that a vector in Rm is just like a function from x to r, right? So we consider a set of vectors which have zero mean, so such that the sum of fi is equal to 0. And we endow it with the quadratic form, which would be a norm, a square norm. Omega of f is the one that we saw before, the sum for I connected to j of f of xi minus f of xj squared. So remember that intuitively, this looks like a smoothness functional. Now, the theorem says that this space endowed with this quadratic norm is an RKHS, meaning it's a Hilbert space of functions that satisfy the RKHS conditions. And so the question then is, what is the kernel of that RKHS? And the theorem says that the kernel of that RKHS is L star, where L star is the pseudo-inverse of the graph Laplacian. Why? So we will explain a bit what is the pseudo-inverse of the Laplacian, etc. But the take-home message here is that you see that we have been able to build a positive definite kernel, which will be the matrix L star. And the way to build L star is not to start from pairwise distances. It's really to start from what is a good space of function that we may want to consider. So here we consider functions with zero average. Maybe this is not necessary, but later we will change a bit this constraint. But more importantly, we define a smoothness functional, which intuitively says that a smooth function is a function such that when two persons are connected, the value of the function should not change too much. So it's encoded by this omega, and from this smoothness functional, we derive a kernel. Again, this means that if we use that kernel with a kernel function, then in terms of functions, we would optimize an objective function like least square regression or classification loss that could be regularized by this type of function. All right, so let's clarify a bit maybe what's the pseudo-inverse and then prove the theorem. So just in case, pseudo-inverse of L is, ideally, we would like to take the inverse of L, right? But as we just said, L is not invertible because it has 0 as eigenvalue. So what's called the pseudo-inverse of L is simply the inverse of L on the subspace where it's invertible, meaning on im of L, and 0 on k of L. This is the definition of the pseudo-inverse. Another equivalent definition, if you prefer to see the equations, is that if you write L, if you decompose L over its eigenvector, so if you write L as the sum for I equal 1 to m of lambda I ui transpose, with the convention that lambda 1 is equal to 0, and the rest are strictly positive, then the pseudo-inverse is the sum where you don't take into account the 0 eigenvalue, so it will be the sum for I equal 2 to m, in fact, of the same eigenvectors, ui transpose, and simply you inverse the eigenvalues. And in particular, one property we'll use in the next slide is that when you multiply L star by L, if it was the inverse, you would get the identity. Now, this is not the inverse because the image of L is not the full space. So it's easy to see that what you get when you multiply L star by L or A by L star is the projection onto the image of L, which, by the way, the image of L was exactly our space capital H that we define in that theorem. Okay? So, proof of the theorem. Why is that space an RKHS, and why is L star its kernel? So the fact that it's an RKHS, here we don't have any problem with the completeness or infinite dimensions, etc. We are finite dimensional because it's a subspace of Rm. So the space, of course, the space capital H is a vector space because it's a closed subspace of Rm. And so the question is just, is omega of f a squared norm? And so we could think in terms of inner product. We could define an inner product between f and g as the same sum, but you would replace the square by an expression in f times an expression in g. Right? So this is what we write here. Is that so? Do we have so we have a vector space? Now the question is this quadratic form an inner product? But here we can use the if I come back here, you see we can use this lemma here that says that in fact the omega of f that we have chosen can be written simply as f transpose LF. So the real question is f transpose LG a valid inner product over the image of L? This is basically what we ask here, so that we have a valid inner product. And the answer is obviously yes, because L is positive semi-definite, and it's even positive definite over its image, because the image by definition is the set where it only is equal to 0 for the 0 vector. So this means that omega, so L, sorry, is F transpose LF is a valid scalar product, and therefore omega is a Hilbert space. And so we know that the norm that Hilbert space is omega of f, the norm square. All right, so now the more interesting property is how did we find that L star is the kernel for that RKHS? And as always, to check that, we need to prove two properties. The first one is that when you fix a node x and you consider kx, so as a function, as a vector over the graph, you need to show that this vector is in capital H. And the second property is that if you fix any node x and any function f, or any vector f over the graph, then we want to check that f inner product kx is equal to f of x, meaning the value of the vector over the node x. So let's prove the first one. The first one is you fix a node x and you want to check the value, the vector kx, and see if it's in capital H. So we have to remember what it means to be in capital H, and it's quite simple here. Capital H is just any vector such that the sum of the entries is equal to 0, right? So what we need to check here is that if you take kx, is it true that the vector kx has a sum of entries equal to 0, which equivalently can be written as kx transpose the vector 1 is equal to 0. Okay? Now, what do we know about k? Well, k by construction is equal to L star. So k is a matrix here, right? The kernel matrix is equal to L star. But so what do we know by the construction, if I come back to the properties of L star, is that L star and L have the same null space. Okay? Because in fact, they are the same function. So one is the inverse of the other over the image, and they both are equal to 0 on the null space of L. So this means that if you take any element of the null space of L, and we know that the null space of L, if I come back here, is equal to the constant vector. We know that if we take the constant vector, sorry, I come back this thing. We know that the null space of K is equal to the null space of L star, which is the null space of L. And because 1 is in the null space of L, we know that the matrix K times the vector constant is equal to 0. And now the matrix K, is the full matrix of pairwise kernel entries. So what we call Kx is just one row of the matrix K. And so because the matrix K times the vector is equal to the vector of zeros, it means in particular that each row of the matrix K multiplied by the vector of 1 is equal to 0. And this is exactly Kx inner product 1. So it's the sum of the entries of Kx. Right, so this proves that Kx is in H. What about the second property? So here we take any vector f in capital H, so any vector such that the average of f is equal to 0, and any node x on the graph. So here, sorry, for some reason I write I for the node. So this is what we want to compute is k. So the inner product between the vector k of x dot and f. And so if we call, again, we want to make this computation for one vector, but we will make it directly for all the i's together. So we'll create a vector, G1, G2, G3, which would be this inner product for all i's, so for all the things together. The reason being that once we do that, it's just more convenient to write it down. Each of these function ki, as I said before, is one row of the matrix K. So here we have a matrix K where each row is something that interests us. And what we need to do is the inner product between this row and F. And remember that in the space capital H, maybe it was in the previous slide, the inner product between two vectors is their F transpose times the matrix L times G. So here we need to compute K times the matrix L times F. And the question is that equal to F? Right? This is what we want to show. Now, the good news is that this is easy because K by construction is equal to L star. This is how we define it. So we have L star L times F. But L star L is the projection onto H operator. So we need to project F onto H. But of course, we started from an F which is in H itself. Okay, so this is F itself. So we have indeed a good reproducing property that F inner product K is equal to F of X. And so, all in all, this allows us to conclude that, come back to the theorem, that space endowed with that norm is an RKHS, and that L star is indeed the reproducing kernel of these RKHS. Okay, so as an example, I repeat the same graph as the one I showed before. And here we just computed L star, right? So there is no difficulty. You start from the matrix L, and then you click inverse, pseudo-inverse, and you obtain this matrix. And so you see it has positive and negative values, but the important thing is that if you use this kernel, you can train a SVM or PCA or whatever, and you know that if you use that kernel, the regularization you will create, so when you formulate your kernel method in your KHS, would involve the particular omega that we saw in the theorem. Maybe something to notice here is that, when we look just at the distances, we said that the Gaussian kernel based on the distances, we said that because 1 and 3 have a distance of 1, and 4 and 5 have a distance of 1, of course, the kernels between 1, 3, and 4, 5 are the same. They were the same before. Now here, if we look at the same pair, we see that the kernel between 1 and 3 is equal to 0.08, but the kernel between 4 and 5 is 0.28, right? So suddenly, the value of the kernel between 2 points does not depend anymore just on how close they are in the graph. In fact, you can, if you think a bit more, you can check that the kernel value between any pair of nodes depends on the whole structure of the network. Meaning that, for example, if you have a huge graph and you just remove one edge on one side of the graph, then it will change the value of this kernel between all the pairs, like even two nodes which are very far away. Of course, it will change it a little, but the value of the kernel between two nodes is not only a function of how close they are locally, but it's also a function of how the whole network is. So what else can we say? Maybe we can try to make the link between, I said we call that the Laplacian, but I did not really explain why it's called the Laplacian. Probably many of you have heard of the Laplacian operator for differentiable functions over R, for example, or Rn. I remember that what's usually called the Laplacian of a function is the sum of the second derivatives across directions. So if you're just in 1D, you can, the Laplacian of f is just the second derivative. And if you assume that instead of having continuous values, you discretize the space, and you wish to approximate the second derivative of f, then it's not a surprise that after a few computations, doing finite approximations, what you recover is, with a minus sign, the L matrix of the graph. So here the graph would be just a linear graph, so a set of nodes which are connected to each other, divided by dx squared for the approximation. Right, but this is fundamentally why we call this L the Laplacian, because it's a discrete equivalent of the continuous Laplacian operator. Similarly, you may say, what about our penalty? If we take the same example, just over a line, here we said we'll look at the sum for I equal 1 to m of fi minus fj squared. So this is exactly our omega of f. And if we assume that we take a linear graph and that f in fact is a continuous function, even differentiable function, then through some standard approximation, you can rewrite this so it converges, if you wish, to 1 over m. Yeah. So there is a scaling factor here, which is not important, but which converges to the integral between 0 and 1 of f prime of t squared dt. Right? So this is something we have seen already previously in the session about Sobolev kernels. This shows, in fact, that what we do with our omega here is the equivalent of a Sobolev norm. When I say the equivalent, is the discrete approximation or discrete equivalent of what we did when we looked at a Sobolev norm over functions. Okay, so in a sense, you could say that the L star is something like a Sobolev kernel, but Sobolev kernel discretized over a network. And of course, here this approximation is just in 1D, and what brings the Laplacian in addition is that this is for any graph, not only a discretization of a line, but any graph, there is a notion of approximate derivative and something like approximate Sobolev norm. Okay, so far we have seen 2 ways to make kernels, and that led to different kernels. One was given a graph, one was compute the distances and try to make a feature space where the graph distances are conserved. And the second was a functional approach where we said, let's start by defining what we think is a good smooth function and see if we can make an RKHS and see what the kernel, the resulting kernel is. Now we'll take a third approach, which intuitively you can think of it as how can we make a Gaussian kernel over the graph, right? So far we have tried to make a Gaussian kernel with distances, but we have seen that in general it doesn't work. The method is not correct. When you take the exponential minus the distance, it's not always positive definite. And for the second regularization, we have seen that we have managed to do something which is nice, which looks like a Sobolev norm. But like in a continuous space, remember that the Gaussian kernel is a bit different from Sobolev kernels. In particular, it creates much smoother function space, like all the functions have infinite number of derivatives, etc. So there seems to be some open question for the moment on how, if we don't want to make just a Sobolev regularizer, but maybe the equivalent of a Gaussian regularizer over a graph, how can we do that? And so to do that, we try now a third approach, which will lead to something called the diffusion kernel, which is to characterize the Gaussian function as the solution of an equation, which is valid on a continuous space, and we will discretize it. All right, so the equation we will use is in fact a super famous equation in partial differential equations, which is called the heat equation, right? So how does that work? Well, we'll use this lemma and not prove it rigorously, but this is folklore, I would say, in analysis. It's a characterization of the Gaussian function as the solution of this diffusion equation, sometimes called the heat equation. So this equation here, if you look a bit in detail, this is an equation where you fix x0, which is a point. Here for a moment, we are just in a continuous space, right? We are back to continuous space, and then we come back to graphs in the next slides. So you fix x0 somewhere, and then you consider a function kx0 that depends on x, which is a position, a parameter, and t, which is a time, right? So think of it as a field of values that evolves over time. And so this equation says that across time, when you have position x and want to see what's going to happen, so the time derivative of the value of the function should be equal to the Laplacian of the field at that moment, right? And so you can think of it, and so there are initial conditions here. The initial condition is that when t is equal to 0, so k is equal to 0 everywhere except on a point x where it's equal to 1. So it's not a function, it's a measure, but this is standard in partial differential equations. Okay, so now the standard result is that if you solve this equation, meaning that at time t0 you're Dirac at a point, and then you wait a little bit according to these dynamics, then the solution at any time is a Gaussian function over the space x, centered at x0, and with bandwidth proportional to t. So sigma square is proportional to t. Okay, maybe an intuition is this is what happens to describe the diffusion of heat. So if you have like a cold space, and at t0 you put some heat very on a spot x0, and then you wait a bit. Then after a few seconds, you look at what's the pattern of temperature on your space, and basically it will follow a Gaussian distribution. Okay, so this is a characterization of the Gaussian function in terms of PDEs. And a natural, so I don't prove it, you can just check at least, forgetting about the technical details about the limit conditions, but that when you take the time derivative and the space derivative, they satisfy these equations. And so what we'll do is just ask the question, what about writing the same equation of our graph? Like I give you a graph, and I ask you to solve a similar heat problem. At t0, you put some heat at a particular node. You assume that the heat can diffuse across the edges of the graph. You wait a few seconds. What's the temperature across the graph after a few seconds? And possibly this, the pattern of this will make a vector of values. And possibly this could be a good definition for the equivalent of the Gaussian kernel. All right, so let's just do that. And in fact, we have all the ingredients, because I remind you that the Laplace operator that is used in the heat equation has a discrete counterpart, which is exactly the Laplace matrix. Right? I mean, it's a definition. We could say, let's define the Laplace operator over the graph as a matrix L, and let's consider the equation that describes the dynamics of a vector ft. So the ft, for any t, it's a vector over the graph. It gives a value for each node. And let's consider the dynamics where the time evolution of ft is minus Lf. Right? Remember that in the diffusion equation there is a plus, but a few slides earlier, in delta was minus L. So this is why we have a minus. All right, so the good news is that this equation is pretty straightforward to solve in itself. Ft is a vector, L is a constant matrix, and the solution of this equation is just the initial condition, F0, multiplied by a matrix which is the exponential of minus TL. Right, this is just solving directly this equation. And so just be careful that here is the exponential of the matrix, right? So it's not a matrix whose entries are the exponential of the entries of L. This is really a matrix defined by a convergent series. So exponential, minus TL, there's a typo here, is identity minus TL plus t squared over 2 times L2 minus t cubed over 6 L cubed, etc. Right, so this series converges, and it creates a matrix called the matrix exponential. And so it's easy to see that the solution to this PDE is this vector. So Ft is a vector now, and it's obtained as the initial vector multiplied by this matrix, where you see there is the Laplacian somewhere, the Laplace matrix L somewhere. Okay, so this suggests that maybe Ft here, if we follow what happens in a continuous space, just like we had, for given t, kt was describing a Gaussian function centered in x0, so it's a good candidate for the kernel between x0 and x. Maybe here we can do the same and say that if we start the heat at a node, any node, so if we start for f0, we say the vector is, we take for f0 a vector of zeros everywhere but 1 in a node. Then when you take the vector ft, fixing, for example, t equals to 1 or 2 or whatever we want, then the vector ft may describe values that would be the value of the kernel between the initial node and any other node of the graph. All right, so this is exactly what we call the diffusion kernel. This was proposed in particular by Rishi Kondor and Lafferty in 2002. And I said here we need to start with a particular f0, which is Dirac, in fact, in a node, in order to obtain the value of the kernel between the node and all the other nodes. And so if you do that for each node in turn, you see that what you will get when you want to write the matrix of pairwise kernels between any point and any other point is simply this matrix here, which we call K. So we could say, let's define K as exponential minus TL. And maybe this is a good, so at least we have reason to believe that this is something that mimics the Gaussian kernel of the graph, in the sense that at least it solves the heat equation. Okay, so now let's focus on this matrix and check that it is. So is it a kernel? Yes or no? And the answer turns out to be quite easy. Yes, it is a kernel, because as a matrix K, if you know that L is symmetric, then even in the series expansion, you see all the terms are symmetric. So exponential minus TL is a symmetry matrix. And moreover, when we expand L over its eigenvector, so when we write L as a sum for I equal 1 to m of lambda I, ui transpose, lambda I are the eigenvalues, ui the eigenvectors, then we know that in this expression, we can write exponential minus TL as the matrix which keeps the same eigenvectors. So we keep ui transpose, and that simply transforms all the eigenvalues lambda I into eigenvalues exponential minus t lambda I. Right? This is a property. If you're not sure, check that. But this is a property of the this matrix expansion. It's called the matrix exponential. Has the property that it doesn't change the eigenvectors, but it changes the eigenvalues through the exponential. All right. So from that, we see immediately that K is a valid kernel, because it's symmetric and it's positive semi-definite, even positive definite, because the eigenvalues of K are exactly the positive numbers, which are the exponential minus t lambda I. So this is a valid kernel. And so if you use it, for the moment, it's not clear what's the RKHS, and we will talk about that later, but at least it seems to be a way to have the discrete equivalent of the Gaussian kernel. At least it's a valid positive definite kernel that solves the diffusion equation. All right, so for information, there are cases where you can compute it explicitly if you want to, to test yourself on how to compute exponentials. Here is the value of the kernel when you have the complete graph or the closed chain. I don't think it's very relevant. What we want to do is to use it on any graph. So for any graph, to compute it, we need just to start from the graph, compute the Laplacian, and then compute typically do the eigen decomposition of the Laplacian, modify the eigenvalues, and we get a new matrix, which is the diffusion kernel. Okay, so let's try now to clarify that, especially, the first approach was a bit different, but the last two approaches, so taking the pseudo-inverse of the Laplacian or taking the diffusion kernel, have something in common. And the thing which is in common, in fact, will allow us to understand a bit better and more broadly the RKHS, and make links also with what we saw before last time, especially over translation invariant kernels. So what we're going to discuss now is prove and explain that both the pseudo-inverse of the Laplacian kernel and the diffusion kernel, so the last two kernels we saw, are particular case of a more general ways to make kernels, which in fact can be better understood in terms of Fourier transforms and therefore what's called harmonic analysis, but this time over graphs. All right, so there will be a small, very tiny introduction to Fourier transforms over graphs, which, if you're interested, I encourage you to look at in more details, because this can be a very useful tool. All right, so first comment, for the diffusion kernel, it was defined as exponential minus TL, and so what we saw is that if you write L over its eigen values and eigenvector decomposition, then you have a decomposition of KT with the same eigenvectors, but with different eigenvalues, right? So in particular, what we see here is that L is not invertible because there is lambda 1, which is equal to 0, but K, so the diffusion kernel, is invertible, right? Because all the eigenvalues are transformed into a strictly positive eigenvalue with the exponential function. All right, so based on that, let's try to write down exactly the square norm in the RKHS of the diffusion kernel, using some transformation that we will explain. So if you have a function f over the graph, so it's a vector, then we see, because the diffusion kernel is invertible, the matrix K is invertible, we can always write f as K multiplied by K inverse times f, right? Because K minus 1 exists. And therefore, we see that f, any function, is in the RKHS because it's K multiplied by a vector, right? So each function Kx is in the RKHS, so when you combine them, it's in the RKHS. So the RKHS of the diffusion kernel is the set of all vectors, okay? There is no constraint on it. In addition, we can compute the norm. So for any function f, you know that if f is written as k alpha, then the square norm of f is alpha transpose k alpha. So here we can write it down by replacing alpha by k inverse f, in order to get that the square norm of any function, of any vector f in the diffusion kernel, kt. I'm sorry, sometimes I put a t, sometimes I don't, but it's the same matrix. So it's equal to alpha transpose k alpha, and if you replace alpha by what we have, you get f transpose k inverse f. All right. So this is the norm. If you give me a set of values over the graph, the RKHS norm of this function is f transpose kt inverse f. All right, so now we can still rewrite this, because we know that the k from the previous slide as an expression over the set of eigenvectors ui, which are the eigenvectors of the Laplacian, and is equal to this equation here. So we can rewrite f transpose k inverse f as follows. If we first project f onto the vectors ui, so this means, the ui's are the eigenvectors of L, so they form a basis of Rn. So for any f, you can first decompose it over the ui's, and you can call f hat I the projection of f onto ui, so the coordinate of f in the new basis. And then if you replace, so in this equation, if you replace k by its value over ui, then you easily obtain that the norm of f square is equal over the, when you write it over the basis, is equal to the sum for I equal 1 to m, so for all the coordinates of f hat I square, right? So this is like the L2 norm of f hat multiplied by exponential t lambda I. All right, and so when you write it this way, it looks a bit like something we have seen for the Gaussian kernel, and more generally any positive definite kernel which is translation invariant. This was in the part called Borchner theorem. This looks a bit like a sum or an integral over some frequencies. So if we see the i's as frequencies, f hat I would be something like a Fourier transform. So the ith coordinate of f onto a basis, and we will see that the basis is in fact a Fourier basis. And we have the multiplication by exponential t lambda I, which mimics what we had when we wrote the norm in the Gaussian RKHS as the integral over the omega, so omegas were frequencies, of the squared modulus of the Fourier transform of f at omega multiplied by exponential of sigma square omega square. Right, so the equation looks the same, and now let me tell you that in fact it's not stupid to see it this way, because the eigenvectors, the ui's, the eigenvectors of the Laplacian are exactly the good basis to do Fourier analysis on the graph, right? In particular, when we project any vector onto the ui's, we get the coefficients which I call the f hat. And this is what's called the discrete Fourier transform of a vector f, right? So remember, the Fourier transform, typically, we have defined it over continuous space. But of course, there is also a discrete version. So usually, when you discretize R or R2, you do a grid, and you compute a discrete Fourier transform. And in fact, what I have hidden, so the eigenvectors ui's form exactly the sine, cosine basis, but discretized. And here we don't even have to have a regular grid. The ui's are by definition what is called the Fourier basis of a graph. right? So this is an important result. When you have any graph, it comes with a Laplace matrix, and the eigenvectors of the Laplace matrix are, by convention, called the Fourier basis, and we will see quickly that they really have the same properties as the Fourier transform. Okay, but if you're with me that there is something like a discrete transform, then you see that here we have an equation that now allows us to see the diffusion kernel as really the equivalent of the Gaussian kernel, in the sense that these are KHS of the diffusion kernel is the set of vectors. So it's all the vectors. Here we don't have notions of C infinity function because it's just finite. But that the norm in the RKHS quantifies the smoothness in terms of how much energy there is in high frequency, so in the f hat I with large i's. And this is, you see that the energy is multiplied by exponential of lambda I. So it's a bit like the Gaussian kernel. It can grow very fast. Like if you have a big graph, the M could be 1,000,000 or billions, a big sum. And so it plays a bit the same role as the Gaussian kernel to heavily penalize the high frequencies in your signal over the graph. Right, so I will not give any more theorems and convince you that this is a good basis, but just visualize with you, when I say that the eigenfunctions of the Laplacian is really what we call, is a good basis, is the Fourier basis. Let us just visualize the UIs, so the successive eigenvectors of the Laplacians, as a function of lambda, right? And here, so I will show a few plots where you have, in fact, we visualize two graphs. On the left, it's a linear graph. So here, imagine that you have, is it 9? Yeah, probably you have 9 connected vertices over a line. So think of it as a discretization of the continuous space, but really, mathematically, it's a linear graph. On the right, it's not linear. You see it has some structure. And so what we will plot now are the values of the UIs. So on the left, the way we'll plot it is that because we're in 1D, it's easy to horizontally keep the index of the node and vertically the value of U. And for example, here you see a flat line, just to mean that the first eigenvector corresponding to the 0 eigenvalue is constant. So this is what we see here. This is a constant eigenvector. On the right, of course, I need a third dimension to show you a signal over the graph. So I will use some colors to illustrate the values that the function UI has on the nodes. And so here, all the nodes have the same value to suggest that, again, U1 is constant. So this is lambda 1, the 0 eigenvalue is associated to the constant eigenvector. Now let's look at lambda 2. So the first non-zero eigenvalue has some values. So here I plot the values, it's 0.12 or 0.76, whatever. But on the left, you see that it does what you want, in the sense that if you did Fourier analysis, the lowest frequency is constant, and then the next one is sine and cosine, which with very small frequency, and in this case, it's just a monotonic signal. So when you project f onto this signal, the first one was capturing the mean value of f. The second one captures the general trend of f. Is it going up or down? Now, interestingly, when you look on the right, you see for a generic graph, you have a similar thing. So here the color code starts popping up. You see that, for example, it goes from red to green. You have a light red at one opposite side and a light green at the other opposite side. So here, the equivalent of being monotonic over horizontal line is to be kind of monotonic over the graph. But you see, it has to choose a structure. So here it goes from, for example, small values on the left to high values on the right. And this is U1, U2. Now let's move on to the next eigenfunction. So the eigenvalues increases. In the discrete case, you recognize that the frequency increases. It looks, again, like a sine cosine with increasing frequencies. And for the generic graph, well, what it decides to do now is to be kind of monotonic in the opposite direction. So it tries, to split the structure in the graph, but it's still very low frequency here. And now I will increase a bit you can play with the slides yourself. I will increase a bit the eigenvalue, so lambda increase in both sides. And what you will see is that on the left, you will have increasing fluctuations. So this is really similar to the Fourier basis, and these are just the U1, U2, U3, etc. for the linear graph. And what's interesting is to look on the right how this translates for a generic graph, and you see that more or less what you have to see is that we started from very flat colors, and we have increasing fluctuations in the colors. So here it goes. More fluctuations, even more fluctuations, even more fluctuations, even more fluctuations, until the last, I think this is, until the last one. And so in the last one, so for example, on the left, you see that this is this is the last U, like the U is the largest lambda. You see that in the line, this is a function that goes up and down and up and down, etc. And similarly, on the graph, you see that there is a very positive, let's say that red is negative and green is positive. So there is a very negative node, which is surrounded by 5 very positive nodes. So it's really like a big change. And then you see that the remaining nodes, they don't become negative, but they are closer to 0. So you have to think that the signal starting from one node is positive, then goes negative, then goes positive, then goes negative, positive, etc. So it's a bit of same behavior. And again, if I come back in the past, we start from very smooth functions, both in the line and in the graph, and we go to higher. So this was a bit long, but a tiny introduction to what's called spectral graph theory, which basically says that what you know how to do on Fourier transforms over discrete signals can be extended to Fourier transforms over networks, and therefore the composition of signals over networks. And so the link with what we saw is that the kernels, so both L star, which was the Sobolev kernel over the graph, and the diffusion kernel, which is more like the Gaussian kernel over the graph, they can both be expressed as what's here. So there are both kernels which are expressed over the Fourier basis. So you always have UI transpose. The UIs are the Fourier basis, so the eigenvectors of the Laplacian. And what both L star and the diffusion kernel do is to replace the eigenvalues lambdas by something else. So for the pseudo-inverse of the Laplacian, we replace each lambda by its inverse, except of course for the 0, 1. And for the for the diffusion kernel, we replace lambda by exponential minus lambda. So what you need to do typically is to, in order to make a kernel, you can make many other kernels as soon as you pick a function R that typically is decreasing. So you want to transform small eigenvalues of the Laplacian into large eigenvalues of the kernel and vice versa. And the reason for that is that just like the computation we did for the diffusion kernel can be done with any kernel that has this form, to derive that the square norm in the RKHS of this kernel, so for any function R, can be written over the Fourier transform of f as the sum for I equal 1 to m of the Fourier transform of f I square divided by R of lambda I. Right? So this really shows that if you modify the eigenvalues in some way, you create an RKHS where the square norm in the RKHS is a modified square norm of the Fourier transform, where you penalize the high frequencies, and you penalize them specifically with the function R. Okay, so R had to be non-increasing. All right, so this makes the link really between the pseudo-inverse of the Laplacian, the diffusion kernel, and more generally, you can invent as many kernels as you want if you have, for example, some prior reason to penalize high frequency or small frequencies in some way or the other. For example, you could say, well, someone told me that I should penalize the eigenvalues with R of lambda, which is not 1 over lambda like the pseudo-inverse of the Laplacian, but I want to regularize that a bit with 1 over lambda plus epsilon, so that in particular, the kernel becomes invertible. There is no problem with lambda equals 0 anymore. This choice would create a kernel that you can write in the eigenfunction space, right? But you can also simplify it as the inverse of L plus epsilon identity. And from it, you can derive what's the L2 norm of any function f in this RKHS. And in this case, you would recover, just do the computation by yourself, it's easy, that the square norm in the RKHS of this kernel, so of the kernel L plus epsilon identity minus 1, is exactly omega of f, so the sum for I connected to j of fi minus fj squared, plus epsilon times the L2 norm squared of f. Right? So this is just one variant, one example, which you can use if you think that this is the good way to regularize. Okay, and all this is a lot of equations, but at the end of the day, it gives you matrices. So taking again the same graph, this is a valid kernel. So here I take the inverse of L plus I. So this is a particular case of this with epsilon equal 1. And the kernel really means that it creates a matrix where the kernel between the node 1 and the node 4 is equal to 0.08. Okay, so you can really compute these things. All right, so I will conclude today's lecture with some ideas for application. I will not go too much detail. There are plenty of papers, plenty of use of these things, but just to try to relate some kernel methods we know with some graph problems we may have to solve. So for example, one problem that's quite standard is if you have a graph, how do you find clusters in a graph? How do you partition the graph into subsets? And so something that you may want to say is, for example, suppose to be simple, we have a graph and we want to split it in two parts in such a way that the two parts correspond to two components which have many connections within the components, but not too many connections between the components, right? So one way to formulate it and to relax it is to say, let's look for a function f that typically would be positive on one side, negative on the other side. So we look for a function f, vector f. We constrain its norm, for example, so the L2 norm to be 1. And among these functions, we would say, well, a good function is a function that doesn't change too much between connected nodes, because we have many connected nodes inside of each cluster. So the sum of fi minus fj, there are many pairs, many ij pairs which are connected within each cluster. So ideally, if we force it not to change too much in dense regions, it means that all the nodes in a dense region will have the same values or the same sign, and therefore we could instead force the change of sign by looking at minimizing the sum of fi minus fj squared, because if it has to change, it will have to change in the regions where there are not too many connections. Right, and I must say that here probably in this slide I realized that there may be a typo or implicit assumption that in fact we should force f to have 0 mean, because otherwise there is an obvious trivial minimizer of this, which is a constant function. So we want to be orthogonal to the constant function, right? Which is exactly the RKHS of the Laplacian, for example. And so if you want to do that, then if you write this equation, then I leave it to you to convince yourself that this equation is exactly kernel PCA with the kernel L star. Okay? You recognize, I mean, you can write it as the norm in the RKHS subject to a unique constraint. So blah, blah, blah. This is equivalent to maximizing the L2 norm of f subject to a constraint that the norm in the RKHS is bounded. And this is really finding the first principal component of the kernel, which is the pseudo-inverse of the Laplacian. Right, so I mean, it doesn't mean it's a particularly good method, but I just wanted to show that to illustrate that there are some problems like graph partitioning that can be formulated as just solving kernel PCA with a particular kernel, which is the pseudo-inverse of the Laplacian. And so, by the way, you may imagine also variance using other graph kernels. Second thing that you may want to do, a typical application, is when you want to do search over a graph. So imagine you have a graph and you have a few nodes that you're interested in. They are like the red nodes here, they are good, and you want to find more similar nodes. How do you rank the other nodes so that you may retrieve the most similar nodes that to the red one? So there are plenty of applications, like just to mention applications in biology, for example. if this is a network of proteins or a network of genes. You may have some information about proteins, like proteins which play a role in some disease. And you may ask, well, I know that these two proteins play a role in a disease, but I would like to check if there are other proteins in this big network that may play a role. And so this translates into, starting from these two proteins, how would you rank the other ones as the good candidates to investigate as possible, being possibly involved in the disease, right? So for ranking, there are plenty of methods, but one of them, for example, would be to say, well, you're looking for a function that is smooth. So for example, looking at the diffusion kernel, you would say, I want a function that goes to 0 at infinity, that is as smooth as possible, and that on the red dots is equal or at least equal to 1. Okay, so you may formulate the problem as what's the smoothest function according to some kernel that in your KHS over the graph, such that f of xi is at least as large as 1 for the query nodes. And if you solve that, then you will get a function that is equal to 1 on the red nodes, and then you will look at this value on the other nodes, and the value on the other nodes would be a way to rank the other nodes by decreasing similarity. So there is no theorem that is good or not, but this is a method that's typically used in applications when you want to find similar and rank nodes in a big graph, given a set of query nodes. Similar application is semi-supervised learning. So this is a case where instead of having just 2 query nodes, you may have a few points of 2 classes. For example, here you have the red nodes and the yellow nodes, and you want to discriminate them, like to predict the colors of other nodes. And similarly, this is just, you want to do that. And one way to do that is just to see that as, binary classification problem, for which you can use support vector machines or kernel logistic regression using a kernel which is derived from the graph. Right? So these kind of things allow you to do graph annotation with kernel methods using standard SVMs or logistic regression. Right. Finally, I don't want to go to too many details, but this last application is a real application in biology, in the study of genomic data, where basically we are confronted with data which can be very high dimensional, but with not too many samples, but where the dimensions is encoded by proteins which are themselves in a graph. So this is a case, and there are many applications like that, where the input you have, so the X you have, are vectors over the graph. And you want to make a linear model of these vectors and use some prior knowledge to regularize. And so long story short, you can look at the size if you want, but if you want to make a linear model and say, instead of just doing ridge regression, like regularize the norm of a linear model, think that the linear model here would be a vector over the graph as well, because the X are vector over the graph, so linear model is a W over the graph. And so you may, as prior knowledge, you may say that you want to control the omega norm of W, when omega is the RKHS norm over the graph. Right, so you can check the size, and there are links to the paper. But basically what it can give you is, for example, this is real data where we trained a model to predict something biological, to classify samples. And so the model is a linear model, so we can visualize the weights of the linear model. And then to visualize the weights, typically what people do, a vector of weights assigns a value to each protein, and then biologists would like to look at the protein weights in order to say something to identify the important proteins. And what it allows to do is, once you map it back, here we have mapped back a model that was trained without prior knowledge over a protein network. And frankly, for biologists, it's a bit hard to understand what's going on here, because you have green and red a bit everywhere. There is no strong signal here. But when you modify a bit of training and use RKHS regularization to enforce that the weight vector is smooth on the graph, then suddenly, by construction, you get a vector that is, let's say, negative in large areas of the graph, positive on other ones. And so it's much in terms of performance, you can check it's slightly better than the other one, but in terms of interpretation, it allows you to interpret globally the role played by the proteins. Like, for example, all this big part is green, so this big part, these are protein kinases, these are other pathways. So you can start saying that you are not sure about the individual values, because here you have forced the smoothness, but at least you can start getting some feeling about what are the positively contributing or negatively contributing proteins in this process. Right. So again, I skipped a lot of details, but here there's a difference between this plot and that plot. And to get the last plot, we use ideas of RKHS regularization in order to train a linear model that has weights which are smooth over the graph. There are similar ideas which have been used, for example, to analyze brain images, where again it's very high dimensional, but when you constrain your models to be smooth over the voxel, so the discretization of the brain, then it allows, instead of being a logical network, this can be a brain image, and gives images much easier to understand and interpret. All right, so we stop here for today. Thanks for your attention. And next time we'll start a very exciting series of lectures about open problems and research topics. Thank you. Bye-bye.